Okay, so H, worded problems. Love them or hate them, these are the things that they're going to get you the mark at the end of the year. So there's some classic examples. If you make sure you do all the worded problems in the book, then they've almost exhausted every single possibility that they can have. So there'll always be one that's something like this. Not that we go on taxis anymore or go into a city. So this here looks to me like it's going to be one of those hybrid functions, two different sections. One bit if it's less than a kilometre, another one if it's more than a kilometre. So there you go, set up the situation. That makes sense. So it's $1.75 and it's here up to and including 1 kilometre. So up to and including, and this is the one if it's greater than 1 kilometre. So find the function which describes the method of payment. Done. Sketch the graph. Done. So we've got our X and our Y. Could have used different words. We could have used like cost and sort of like kilometers and all that sort of stuff. And notice that it's pretty obvious here that this point here is $1.75, even though I haven't marked it. That's one, but they've marked another point here just because, you know, there's nothing else on this graph. So they've just marked another point there. So just take care with doing something like that. This one here, you would have seen loads and loads and loads of these before. So volume, length times width times height. So the dimensions of the box, 24 minus x. So if you 24 minus 2x, because that whole distance there is 24, that little distance there is x, that little there distance is x, so you got 2x's. Same with our width and our height. When that's folded up, our height or depth or whatever you want to talk about, the box becomes x. So there's a volume of our box, length times width times height. So you're multiplying those three things together. So find a function which gives the volume of the box in terms of x. So there's our function, and state the domain of the function. So if we look at each one of those things and break it down, that one there's telling us that x has to be less than or equal to 12. That one's telling us that x has to be less than or equal to 9. That one's telling us that x has to be greater than or equal to 12. So because x has to be less than or equal to 9, we can, you know, that one is sort of irrelevant. It has to be between these two. So the domain is between 0 and 9. There's the complete graph. So if you type that in, you get that. But obviously between 0 and 9, we want just that bit. So that's our actual graph. I didn't ask you to draw the graph. I'm just highlighting graphs. Okay, this one's a real pain, and there's lots of little things, little tricks that you might think, I would never think to do that. I would never think to do that. If I hadn't seen this, I would never think to do that. So you've got to kind of open up your mind and really think a little bit laterally. So it's isosceles triangle, rectangle drawn inside. Find it says an area. Okay, so there could be sort of because that you know that rectangle could be like that. It could be like that. Yeah. So this is just so it's going to obviously have x's and y's in it or whatever letters we decide to choose for it. So the height of the rectangle y and the width 2x. So before we do anything else, I want you just to have a think, maybe stop the video and think, okay, why is it not just x and y? Why have they picked 2x? Okay, hope you're back. So the clue is drawing a line down the middle. So if we draw a line down the middle, y 2x. So basically that means we can work out the area where it's x by y, and then we can just double it, can't we? So Pythagoras' theorem, if we want to work out that height, it's 15 squared minus 9 squared, all square rooted, yeah? So the height of this triangle is 12. I think we could work that one out. So let's have a look at this. So we split this up. We're only sort of looking at one half of it, yeah? So this is the actual question that they're asking. Find the area, find an area of the rectangle function and state its domain. So we're going to look at similar triangles here. Okay, so we've got triangle AX, AYX. There you go, AYX. Good highlighting, sir. Is similar to the triangle ABD. So those two triangles are similar triangles. So basically what we're saying is X. So it's the small triangle the base of the small triangle divided by the base of the big triangle is going to equal the height of the small triangle. So that's 12, take away y, isn't it? Divided by the height of the big triangle. So that's, once we've set that up, our algebra now shouldn't be too bad. So do a bit of rearranging, end up with y equals. We could have rearranged it to say x equals, we just rearranged it to say y equals here. So don't forget, the area of this rectangle is going to be 2 times x times y, isn't it? It's 2x times y. So we can just, there's the triangle. There's the rectangle. So now we can just say area equals 2x times y. So we've rearranged that to say y. Remember, if we'd have rearranged it the other way, we would have just, our substitution would have been a little bit different. Okay, so we found the formula. So for the rectangle to be formed, x either has to be greater than or equal to 0, or that has to be greater than or equal to 0. So do a bit of work with that, and that's telling us that x has to be less than or equal to 9. It's telling us that it's between 0 and 9. So the domain is between 0 and 9, and the formula is that, which is just that multiplied out, isn't it? It's just that multiplied out. So there's our formula, and I've probably drawn a graph. Yes, I have. I've drawn a graph. So 7 questions there. Make sure you do them all. Mr. Patch, over and out.